Hi everyone, my name is Yiannis. I'm a co-founder in a company called Selfie Networks, and today I want to talk to you about network tokens and how we leverage eBPF to build token-based functionality for Linux environments. So what is a token? It's essentially a streamlined mechanism to transfer metadata between endpoints or between an endpoint in the network in a secure and scalable way. You can think of these as JOT for the network, and they are tailored for use by infrastructure and network teams. Network tokens essentially include a set of arbitrary claims, which are then cryptographically encrypted or signed to provide properties around integrity, authenticity, and confidentiality. They expire, so they have a short lifetime, and they can be bounded to certain fields like the source IP address to account for replay and spoofing attacks. There are different use cases where we can use tokens, just highlighting a few here. We can use them to secure existing metadata. For example, we can wrap the overlay ID of a virtualized workload with a token in order to provide integrity and authenticity guarantees. We can use tokens to extend an OpenTelemetry identifier to the network layer to have better visibility on the life of a flow. We can use tokens to access policy-based forwarding and network SLAs, or we can use them to do directly access control based on metadata encoded within tokens. I'll use the last application to describe how we use eBPF to implement the application, but they all share very common characteristics in terms of the overall architecture. So imagine that we have two hosts. Host one is a backend node running in production, and host two is a front-end node running in production again. And what we want to do is make sure that only backend nodes can access the front-end nodes on the right side. And so essentially, every token-based application has two basic packet operations. One is insert a token at the egress with the necessary metadata, and then inspect this token at ingress and verify that it's valid, match it against the policy, and take the desired action. Here, as you can see, we are inserting a token where we are defining the metadata associated with this node. There is an expiration time and a bound IP, and this is encrypted with a certain algorithmic key and sent out. And on the ingress, we are just decrypting the token with a predefined key, and then look at the metadata, and if the metadata matches, we let the packet go to the application. How we use eBPF to implement insert and verify capabilities. Essentially, inserting a token is straightforward. We use a TC egress program. We store a pre-computed token into an eBPF map along with the policy, and based on that, we decide whether we should include a token to an outgoing flow, and if so, what token should that be. We also use the capabilities of eBPF to expand the buffer, adjust length, checksum, and so on and so forth. On the ingress side, we do something similar. So we have a TC ingress program, which we use to detect and verify the token. Again, we use maps to store the policy and the metadata to match against, and if the token is valid and the policy matches, we let traffic go through, otherwise we reject it. One note here is that part of verifying a token is implementing a crypto operation. Right now we don't do this with eBPF at the kernel, but we use an XDP socket to make the buffer available from user space, where we use publicly available JOT and binary token libraries to do the verification there, and then re-inject the packet into the kernel stack. What are the benefits that we get from eBPF? We can transparently inject and verify tokens in multiple layers. We can do all the plumbing, change length, change buffers, add extensions with no application changes and no kernel customizations. We can redirect to user space in a very flexible manner, so we can do this only for the packets that contain tokens. It would be much better if we could do this using the kernel script API. So if there is a wishlist here, better crypto support within eBPF would be one thing to add. Another big benefit is that we can use the same code for both host-based applications and network or gateway-based applications. That allows us to do things at a single code base. And lastly, we can sort of like expand the initial model of injecting metadata on the side by exposing a direct API for applications to insert their own tokens using custom socket options. That's all. If you have any questions, feel free to ask now or send me an email. And you can visit networktokens.org where you can find the spec and relevant code. Thank you very much.